Hello everyone. Today we're going to be talking about Taylor series and Maclaurin series, and we're going to talk about how they were derived and how they work. So let's get right into it. Alright, so before understanding what a Taylor series or a Maclaurin series is, it's important to understand what a polynomial is. So let's write that down. So a polynomial is simply just a coefficient times your variable x to the power of n, where n is any whole number. So that would be, this would be your coefficient. And that's where, oops, and then let's write this. So a can be any real number. So it's not limited by n as whole numbers. It can be anything like pi, negative numbers, or anything. X is just your variable for your function, and then n has to be a whole number. So we're going to do the same thing here. So this is your exponent. And that's going to be n, comma, and then it's going to be like this. Oops, that's not a good W. So there you go. That's what a polynomial is. So exponents has to be whole numbers. So that's 1, 2, 3. Oh, and then also 0. 1, 2, 3, 4, 5, and then 6, and then so on. Where a can be any whole real number. All right. So why is this important? Well, it turns out polynomials, one of their traits is that they are always continuous. So that means there's going to be no points of discontinuity, no asymptotes or any imaginary numbers like the square root of x or 1 divided by x. Those have discontinuities, but polynomials do not. It's if you have an elementary function of polynomials, then you will never have a discontinuity. As long as your rules here are respected, like any whole number. Another big aspect of polynomials is that they're eliminable. You can eliminate them. So what does this mean? This means that if you take the derivative of them, you can effectively remove them from a function. And this is one of the most important things about Taylor series, because Taylor series are made of polynomials, and they're only possible because one of the reasons why they're possible is because of polynomials and how the terms can be eliminated. And another attribute of polynomials is that they can be equal to 0 with only one term. Now this might be doesn't really vague, but it'll become more evident later. So for example, e to the power of x can never equal to 0, excluding limits, and of course. And we're going to go elaborate over this being able to eliminate polynomial terms. So polynomials, they're kind of constant-like. And what I mean by this is the following. So if I were to ask you to take the derivative of some constant, c for constant, this would always be equal to 0. Oops, I forgot to make this a yellow. This would always be equal to 0, where c is any real number. And this is very similar for polynomials, because if you were to take the derivative of just, let's say 2x, so that would be 2x. Then if we apply the power rule, this would just become equal to 2. And if we took the derivative again, well, you just notice that it's a constant here, and it would loop around here. So we just eliminated this term if we took two derivatives of it. So this comes back to the idea that they're eliminable. And they're constant-like, where you can, if you have a constant, the next derivative, it'll just disappear. And this is for any polynomial as long as you respect polynomial rules. So, right, if you were to take the function x to the power of 4, then if you took 5 derivatives of this, it would actually become 0. So that would be d over dx, and this would be to the power of 5. Right? This would collapse to 0. And in fact, if you can notice pattern here, it would become, if you take the derivative of a polynomial, so d over dx of f of x and let's say n here is your derivative amount. So if n is equal to 0, that's your original function. 1 would be your first derivative, 2, the second derivative, and so on. So it turns out this would always collapse to 0 whenever your exponent here is just n. Oh, let's zoom in a little bit. N, and then orange, plus 1. And that's the same up here. And this only applies to polynomials, of course, because they're eliminable. You can eliminate them, whereas other non-polynomial functions cannot be eliminated. So here you go. And you can test this out, and you'll find that this is true. As long as it's n plus 1, this will be equal to 0. And if you keep taking the derivative of 0, it'll always be 0. So that's the idea, that they can be eliminated, right? And collapsible. So if you, let's just expand upon this. So non-polynomial functions, for example, square root of x, or the natural log of x, or an exponential function. And these all break the polynomial rule in one way or another. This has a fractional exponent, right? That's x to the power of 1 over 2. That does not respect whole numbers. Natural logs are just a whole nother dimension of inverse functions. And then exponentials, I mean, the exponent isn't is a variable instead of being just a whole number. So that's why these are not polynomials. And if you were to take the derivative of these functions, for example, square root of x, that would be so if we were to take the derivative of this, so let's just say if we go down 1 for all these functions, square root of x would just become 1 over 2 times the square root of x. And this would be your derivative. And you see here that the square root of x is preserved, right? It remains the same. And if you were to take the derivative again, nothing would change. So you can actually eliminate it. And that's the same thing with the natural log. Oops, wrong color. So this would become just 1 over x using just derivative identities. Right? And if you take the derivative of 1 over x again, so if you take the second derivative of natural log x, this would become negative 1 over x squared. So, yeah. And then e to the x, well, it just becomes e to the x. If you take the derivative, it's a famous identity. So then this would just become, let's go like this. Actually, no, let's keep it the same since it stays the same. Right? And if we keep taking derivatives, it's preserved, doesn't collapse to 0 like a polynomial. So let's just write it down here. Non-polynomial, non-polynomial functions cannot be eliminated / collapsed through taking any amount of derivatives. And this is a massive rule in understanding a Taylor series. So let's give that a yellow star. All right. So then I'm going to ask the next question of what makes a function different from another one, right? And this might be obvious, but it's still important to go over. So let's just separate that. So let's say you have two functions, arbitrary functions, right? This is your y and x axis. So let's say your first function is just some cubic function that looks like this, right? And then the other function is just a parabola. And I ask you, what makes these functions different? What makes blue different from yellow? And the answer might be evident, and that's just how these have different slopes and curves to them, right? This one's kind of like a happy face, and this one's a happy face, but then it goes back down. And you can tell the difference because they have different curves. Yeah. So, if you were to take the derivative of these, you would evidently see that they have different derivative values. And if you're to take the derivative of that, again, it would be different. So the answer to our question here, let's just answer it because we did ask a question. So the answer is slope and rate of change. So let's say yellow. So yellow is equal to f of x. And light blue here is equal to g of x. So they're evaluated both on the same variable, but they're different because of their curves. Right? So evidently here we can see that f of x, oops, and I made a mistake with that. F of x is not equal to g of x. right? And if you were to take the derivative of both functions, it should also reflect that. So let's just write that down. So the derivative of let's just write this, derivative of f of x is not equal to the derivative of g of x. Right? And if you were to take the derivative again, they shouldn't match. So with this question and answer and a bit of train of thought here, we can see that functions can be have an identity based on their derivatives. So function So as we see here, right, these have different curves, and we took the derivative of it. And if we were to take the derivative of it, we could tell that they're not the same because they have different curves. So that's what we're saying here. A function's identity is based on their curves, right? If they have the same curves, then they have the same derivatives. But if they have different curves, then they must have different derivatives. So that's their identity, right? If you have blue eyes and someone else has brown eyes, then you guys are different because of your different eye colors. You have different parts of your identity. And that's kind of the same thing with functions. So we can expand upon this by saying, well, if every function or every derivative, pardon me, if every derivative is the same, then you must have the same function. Right? If you were a complete clone of your friend, then you'd have all the same attributes as them, so you must be the same person. And that's the idea here. So let's write this as an equation. So before we do that, let's consider A and B. And if I give you the equation A minus B, and I told you this is equal to 0, then just through some algebra you can tell me that A is equal to B, just based on this statement. Even though A and B are two different variables, we can just tell you that with this equation. So let's use this idea to build our little formula that tells you that explains or represents this explanation that we have here. So if we have f of x minus g of x, yeah, no, that's good. And this is equal to 0, then we must have the same function, right? If f of x was x cubed, and then g of x was x cubed minus x cubed would equal to 0. So that's just showing that this identity works, right? But if g of x was slightly different, like x cubed minus x squared, then it would not be equal to 0. It would be actually equal to x cubed minus x squared. So these don't actually fully cancel out. They don't collapse. All right. Well, let's expand upon this idea. if two functions are the same, then all their derivatives must match. So if f of x minus g of x is equal to 0, then that means that f prime, let's just use this blue here, f prime of x minus f prime, or g prime of x, must be equal to 0 as well. Right? And then we can do this again. F double prime of x minus g prime of x is equal to 0. Right? And then do this infinite times, and if they're all equal to 0, then you have the same function, right? If they're both if their curves are based on derivatives and all their derivatives are the same, then it's the same function. So let's put this into a summation notation. So, if the summation of n is equal to 0, let's represent n by purple, n is equal to 0, and upper bound is infinity. I could make a prettier one. That's better. Bracket f of to the power of n, and then bracket x minus g of n, bracket x, then if this is equal to 0, then we have the same function. And let's write that down in yellow. Then f of x is equal to g of x. So oops. Right? So we're just saying if all their derivatives match and it's equal to 0, even if one little derivative doesn't match properly, then this would not be equal to 0. But if all of them match, all your identity pieces match, then they must be the same. And we're just pretty much saying what we're saying here and up here. So this should hold, or x here, x up here. Actually, that's a little too far out. X should hold. Actually, I don't like that S. Should hold. Right? So if you were to substitute 4, so f to the power, or f derivative n of some value, and if both functions are the same, then they should equal to 0. So we can just substitute x with some number, and this rule should still be respected. All right. So with this idea in hand, where a function can be, its identity can be based on its derivatives, right? Then what if we were to mimic all those derivatives? So let's get into this. And this is really the idea of a Taylor series. So let's go in Coral. So can we try and mimic the derivatives of a function we want to make? To effectively clone it? or and the answer to this is yes. That's what a Taylor series does. So we can pretty much build any function we want by just cloning its derivatives, and we actually express it. So the answer to this is yes. And an example of this is the sine function. Let's put the x in yellow for consistency. Right? Sine x, you can't just express it with a combination of radicals or natural logs, right? This is a function that you know in your mind, but you don't know how it's actually represented. And you know its derivatives through your calculus classes, but what is it? What exactly represents it? And that's what a Taylor series can do, because you know all of its derivatives, so you actually know its identity. You know what makes sine of x. So all we need to do is just mimic its derivatives to pretty much build it. And the way we're going to do this is using polynomials, and that's why we elaborated over a polynomial, because of their characteristics: continuous, eliminable, and can equal to 0 with one term. So that's why we use sine x. Or not sine x, but polynomials, pardon me. And for this, we're going to use a Maclaurin series, since it simplifies a lot. And we'll elaborate over it later, what a Taylor series is. So Maclaurin series. So a Maclaurin series is basically defined as the following. M of x, where m is just, I don't know, Maclaurin, just to represent that, just a function. And this will be equal to c of 0, so c for constant, plus c1, another constant, different from c0, times x plus c2 times x times x squared. And then that's going to be plus c3 times x to the power of 3 plus c4 times x to the power of 4, and then so on. So on, right? Keeps going as this. So this is pretty much an infinite series, in fact. All right. So what is this polynomial here means? It's a polynomial, right? Because x c2 is a coefficient, right? Like established above with a. And you'll see that n and our function down here are all whole numbers. So this is a polynomial. And I just realized I used the wrong color here. So going back to our idea, if we mimic a function with all our derivatives being equal to the same, then we've built the same function, right? If we respect our rule up here, if all our derivatives remain the same, are all equal to 0, as we said here, f of x is equal to g of x. And this isn't an absolute, since there are caveats to this. It gets weird with absolute values and building piecewise function like with derivatives of absolute values, but that doesn't really destroy our hypothesis here. So let's represent one of our ideas of characteristics of polynomials. So if we were to take m of 0, so we'll just use yellow because now x is equal to 0, right? X is equal to 0 in this case. Right? You'll notice that it becomes C0 plus C1 times x, but x this time is actually just 0. Then that's going to be the next term. Times 0 squared plus C3 times 0 to the power 3. And then plus C4 times bracket 0 to the power of 4. Dot, dot, dot. It continues like that. And you'll notice that C0 isn't attached to an x, but all the other terms here are. And anything times 0 is equal to 0. So C1, no matter what number it is, 4 million, 0.456 pi, doesn't matter. That times 0 will always collapse to 0. So all these terms after C0 just collapse to 0. So these terms collapse to 0. All of them collapse to 0. So it's effectively C0 plus 0 plus 0 plus 0 plus 0. And this just simplifies. You don't need to write all these C0 plus 0 plus 0. M of 0 is just equal to 0. Or sorry, M of 0 is equal to just C of 0, sorry. When it's evaluated, of course, at 0, only at 0. So we just isolated our variable C0. And here, we can mimic the 0th derivative of a function. So, again, this is another reason why polynomials are special, right? Because if we set x is equal to 0 here, all the other terms just cancel out. And that brings back our idea of, where was it? That can equal to 0 with one term, right? If each term was actually just an exponential, so some e to the x or 2 to the power of x, if we set it to 0, then that would actually be equal to 1. There's no way for any exponential to be equal to 0 without using limits. So that's one of the special things about polynomials, and that's why they use them in Maclaurin series and Taylor series, right? That's pretty important. And now we're going to use another important part of Taylor series and Maclaurin series, why they use polynomials, and that's because of you can eliminate them. So let's take the derivative of our m of x, Maclaurin of x, you can say. So let's just divide this just to make it clear. So m prime, let's use purple, m prime of x and then this is just equal to, and if we were to apply the power rule, you'll see that C0, well, as I set up here, C0, derivative of any constant, it will always collapse to 0. So that C0 disappears. And then using our power rule, right, so C0, so that would be equal to 0, let's just write in purple because that used to be C0, plus C1 times 1, right? Because the power rule and the x collapses to just 1. Again, collapsibility, right? So we just deleted the x here. And this wouldn't be possible without polynomials. If we used square root of x, the x would have lingered there. But because we're using polynomials, it disappeared, right? They're constant-like. All right, so plus C2 times 2 because of the power rule, right? The 2 comes down, and then this becomes times x because the x, times x because the 2 came down and it just gets reduced to 1. So let's just write a 1 just to make it simpler. And then let's keep writing, plus C3 times, guess what? 3 times x to the power of 2. And then let's just do one more if it hasn't become, if you haven't noticed the pattern yet, plus C4, constant 4, times 4 times x to the power of 3. And then this just continues. And we can use this again of m of 0, but instead of m prime of 0. And you'll notice if we do that again, m prime of 0. So this is just equal to C1. Just everything else just collapses to 0. C2 times 2 times 0, 0. C3 times 3 times 0 squared, 0. And it collapses all the way. Again, polynomials can be equal to 0 just with one term, unlike exponentials. Yeah. And then also they're eliminated. We eliminated the x in the original function. When we took the derivative, it disappeared because of the power rule, which you cannot do with other functions. So before going too far, let's actually work with real numbers, right? Not just variables. Let's try to build sine of x actually, using this idea that mimicry. All right, but we're gonna still use what we just learned here. We're just gonna use actual numbers so it can be understood better. So let's define that. Okay, so let's just say f of x is equal to sine of x. Sine of x. Right? This is the function we want to mimic. Let's mimic all its derivatives as we said in this rule right here. Okay. So let's just start with our first step here. I'm not going to write that all down again. So let's just copy this all the way down there. So hold, copy, and then paste. Beautiful. Okay. Now we want the 0th derivative to match, right? Again, that summation piece that we built there. Let's use that. Let's exploit that. All right. So what is sine of 0? Sine of 0 is equal to 0. Simple. Okay. So now we set m of x equal to 0. And then that will just leave us with C0, right? Because everything else collapses as we said before. Now we want our 0th derivative to match, right? So m of 0 is equal to c of 0. Well, we want m of 0 to be equal to 0 as sine of 0 is equal to 0. So that means C0, let's write this in a different color, C0 here must be equal to 0 to preserve that identity right there, right? Got to have the same hair color, right? Okay, so now we've just matched the first, the 0th derivative. Okay, well now let's take the first derivative. So, m prime, actually we already wrote it up here, so no need to do that. So, m prime. Alright, gotcha. Copy. And then paste. Beautiful. Okay. And we'll just separate this by a nice white line to show that this is our next derivative. So m prime of x. Well, let's do this again. We want, now that we're derivative, we took the first derivative of m of x, that means we have to take the first derivative of sine of x. Well, what's the derivative of sine of x? Cosine of x. So let's chicken scratch that. So, okay. Running kind of out of space here, but that's fine. So sine of x, derivative is equal to cos of x, cosine of x. That's our first derivative, right? And since it's centered around 0 here, what is cosine of 0? And this is cosine of 0 is equal to 1. All right. Well, now let's do the same here. M prime of 0, where x is equal to 0. Okay. Again, this idea that everything else collapses, that leaves us with just 1 times C1. And everything else collapses, right? Because everything else is set to 0. And then that 1 times C1 is just C1. So we can remove this. But this will come and haunt us later. All right, so m prime of 0 is equal to C1. Well, we want m prime of 0 to be equal to 1, right? Because of our identity, we're trying to match the identity like at summation. So that means C1 must be equal to 1 to preserve that identity that we set. So let's just write that right here. So C1 is equal to 1. Okay, beautiful. All right, now let's step into uncharted territory. Let's take the next derivative since we've finished with this part. Alrighty. Okay. So let's start like last time. Actually, no, we should be fine. M, second derivative. So let's continue for the second derivative of m of x, Maclaurin of x. All right. So that becomes m x is equal to, that'll become 1 times 2 times C2 times, or plus, sorry, 3 times 2 C3, times C3 times x. Actually, we don't need to write the x there, or the times symbol. To the power of just 1, we can just write that like so, just to make it obvious. Plus 4 times 2 times C4 times x squared plus, and so on. You should get the pattern by now. Right? And where did I get all these numbers, right? So we take the second, or the first derivative, and we take the derivative of that, right? And that becomes that c1 goes away since it's a constant now. It's just m prime of x c1 plus all the other terms. And we take the power rule. So c2 times 2 times x, that x just disappears. So that becomes 1 times 2 times c2. That 1 times 2 is just 2, 2 times c2. And then we take that 2 down from right here. So that becomes 3 times 2 times c3, x to the power of 1, and so on. Just using our power rule, right? And let's just follow the steps we did before. So what's the derivative of cosine x? That is minus sine x. Actually, let's just use an orange here to drive that, right? Minus sine x, right? That's the derivative of cos of x. Okay, well, let's do the same thing. Minus cos of 0 is equal to, well, 0 minus 0, which is just 0. So let's write that down. So that's, now let's go to the next step in our little routine here, and double prime of bracket 0. All the rest collapses because everything times 0. I love polynomials. This just becomes 1 times 2, 2. So that becomes 2 times c2, right? Okay, and we want 2 times c2 to be equal to negative cosine of 0, or 0 to match the derivative of that, right? We're mimicking. We keep mimicking. So then this becomes, well, 2 times what? C2. 2 times what is equal to 0? Well, that means C2 has to be equal to 0. Right, let's just write the algebraic expression down. So 2 times C2 has to be equal to 0. And then we divide it by 2, so C2 must be equal to 0. And let's write that down here. Is equal to 0. Okay. Let's do another step. We'll do one more after this one. Actually, yeah. 2 more. All right. Now let's do m triple prime of x. And I'm not going to bother by writing all the other terms. Actually, no, I will do it one more time. Alrighty. So then it becomes 3 times 2 times 1 times C3 times x, but that x up here collapses, so it's actually not times x, sorry, plus 4 times 3 times 2, okay? And then that's times our friend C4. X to the power of 1. And this is plus. So these are cutting quite a bit bigger as we add derivatives because of the power rule, how they come down. But we are eliminating terms, right? Right? This C4 at the beginning would have been x to the power of 4, which actually we didn't write, but it would have been x to the power of 4. But as we've taken more derivatives, it's shrink, and actually if we take the derivative of this, it'll disappear. All right, so let's just write this one more time. So that becomes 5, times 4 times 3 times, let's go C5. And that's going to be x squared. And then dot, dot, dot. Okay, let's keep following our steps. All right, derivative of, ooh, I made a mistake here. It should not be negative cos x. It should be negative sine x. All right, the derivative of negative sine of x is negative cos of x. So that becomes negative right? And then let's evaluate it at 0. Mimicking. We're not mimicking yet actually, but we're finding out what we have to mimic. Minus cos of 0, this is equal to -1. Wrong color, oops, is equal to -1. So that means, let's evaluate m triple. Of 0. Right? This will just be equal to 3 times 2 times 1, so that'll just be 6. But we can actually write this, if you haven't noticed, these are becoming factorials. So 3 times 2 times 1, before that it was 1 times 2, and before that was 1. So that these actually become factorials. So that becomes, let's write it, 3 factorial, okay, times C3, right, and then the rest collapses, right, plus 0, plus 0, plus 0, all right, and we want 3 factorial times C3 to be equal to, to be equal to -1. So what does C3 have to be equal to make that statement true, right? And let's calculate mimicry. Gotta keep that, yeah. Okay, so let's do the simple algebra. C3 prime, C3 equal to -1. Okay, we bring this, divide it, right? And we'll find that C3 must be equal to -1, or just -1 over 3 factorial to preserve our mimicry, right? If C3 has to be equal to this to be mimicking minus cosine of 0, right? So, yeah, so here you go. So if we sub this in, -1 over 3 factorial for C3 here, the 3 factorials will cancel out, and that will actually be equal to -1, which means m triple prime of 0 is equal to -1, which mimics minus cosine of 0, which is equal to -1. So we're matching derivatives. Again, matching our rule. I keep repeating this just to get this identity idea in your mind to make it make sense. And that's what we're actually doing right now. Okay, let's take the fourth derivative. And this time we'll just be lazy since we're noticing a pattern. Okay, so m to the power m of fourth derivative. Oops, I cannot write right now. Oops. Okay, Roman numerals of x is going to be equal to C4 and we write that as, actually it would be 4 factorial, right, following that idea, times C4. Okay, and that's going to be plus 5 factorial divided by 1 factorial times x, or times, sorry, we need our constant, C5 times x, right? And then our next term here becomes 6 factorial divided by 2 factorial times C6 times x to the power of 2. And then let's do this one more time. This becomes 7 factorial over 3 factorial times C6, or C7, sorry, x, wrong color, x to the power of 3. And then triple dots. All right, and then let's find our derivative. And something big happens here. So derivative of minus cos x is sine of x. Okay. And this is pretty substantial because the derivative of minus cos x is sine x, as I said. And we've just came full circle, right? We started with sine, then we found the derivative, right? Cosine, then negative sine, then negative cosine, and we just came full circle. So there seems to be a pattern to all these derivatives for this specific function. This won't be the case every time, but this is pretty interesting that you have a circle of derivatives, it looks like here. All right. Well, let's move on. Sine of 0 is 0. All right. So what does that m to the power of, not power, but derivative equal to? So m derivative 4 of 0 is equal to, the rest collapses, 4 factorial times c4, and then plus 0 plus 0 plus 0. And this, we want this to be equal to 0, so that becomes, let's use, again, basic algebra. So that becomes 4 factorial, correct? Just making sure here, 4 factorial. 4 factorial here times c4 must be equal to 0. Isolate for c4. c4 is equal to 0. Oops, wrong color again. And did we do that up here? No, we did not. Let's just write that. Okay. So now we can generalize this. So, all right. And for the last step here, let's just do m. Let's divide it one more time. Okay. m5 of 0, or of x, we're not there yet, is equal to, we don't need to bother with the rest because we know that it's going to be equal to 5 factorial times c5 plus the rest. So we'll just do plus dot dot dot, you know what comes next. Okay. Derivative of sine x, well, since we're coming full loop, the derivative of sine x must be cosine of x, okay? Okay, cosine of x. So then cosine of 0 is equal to 0. Or, sorry, cosine of 0 is equal to 1. So let's express that here. Derivative of 5 x. Oops, not x, it should be 0. Is equal to 5 factorial times c5, and we want that to be equal to 1. So then let's do our little algebra. So that becomes 5 factorial times c5 is equal to 1. Let's use, this color. And then we'll find that c5 is equal to 1 over 5 factorial. All right, I think we collected enough data. We've done enough examples. So let's write down what we've learned. So C0 was equal to 0. And C1 was equal to 1. C2 was equal to 0. C3 was equal to 1 over 3 factorial. So it was negative as well. So it would be negative 1 over 3 factorial, right? Yes. C4 is equal to 0. And C5 was equal to 1 over 5 factorial. And there might be a pattern you can notice already. It would be better to do more terms, but it takes a long time, especially when you get deeper and deeper. But there's a noticeable pattern here that it alternates from 0 to some number to 0 to some number to 0. And another pattern is that it goes from a positive number, then a negative number, then a positive. And I'm sure that keeps happening. That'll keep happening if we keep doing terms. So another thing you can notice is that the factorials here increase by 2. So negative 1 over 3 factorial, and then it becomes 1 over 5 factorial. So that factorial increases by 2. And this is also explainable by here, because this would be actually 1 over 1 factorial, which is just 1. So we can actually make predictions. So let's just do this in a different color. Let's go for dark blue. So C6 should be equal to 0. C7 should be equal to a negative number, since the last one was positive, 1 over 7 factorial. And let's just do 2 more. C8 should be equal to it should be positive, or it should be 0, since the last one was a number. And then C9 should be equal to a positive number this time, 1 over 9 factorial, and then so on. All right, so now that we've written all this out, before continuing, that pattern we noticed where 0, 1, 1, 0, then it keeps alternating from 0 to some number. And the reason why that is because I want you to notice something very interesting here. So we started with a sine x. We didn't write it here, but that's fine. So then we took the derivative, which became cosine of x. And then we took the derivative again, minus sine x. And then we took the derivative again, minus cos x. And then we took the derivative again, and we got to sine x. So we came full circle here. And that's something neat about the trigonometric derivatives, is that they come full circle. And we can see that here, and that's why we're going to be having repeating zeros alternating every time, is because this will continue to loop, and sine of 0 will always be equal to 0. And that's why we see those zeros there that keep repeating. So actually, let's just write that down. I call this the trigonometric loop. I don't know what it's actually called. It's just something that I've noticed. So we started with sine x. And then it became cosine x. Right. Yep. And then it became negative sine x. And then it became minus cos x. And if you take the derivative one more time, you loop right back to the beginning. And this is what I call the trigonometric derivative loop. So down is each one derivative. And that's what we're observing right here. So if we were to take the derivative again, sine x would become cos x. And that's why we see this pattern also of negatives and positives, because we go from positive and then we skip cosine because, we skip sine is equal to 0, cosine is equal to some number. When we cosine of 0 is 1, and then we get to a negative here, but then we skip the negative. So actually all that we're interacting with here are these two terms here. And that's why it jumps from negative to positive, because this one is a positive number and this one's a negative, and that's why we see that in our results. Okay, so with that, let's write this into our original formula, and it'll allow us to see patterns, more patterns. So remember our original m of x, we're going to plug in, since we know what these c values are equal to, let's plug them in. All right, we're not going to write too much since they take a long time to write, but you get the idea. So m of x is equal to, well, we found c0 is equal to 0. Okay, and that's going to be plus, right? This was originally, actually let's do this in purple. Oop, that's not it. That is not purple. This was here originally c0, but we found that it's equal to 0 for sine x. Okay, so what was the second term? c1 was 1, so then we do times 1, and then that's going to be times x. Okay, and then we're going to do plus c3, or c2, sorry, so this was c2, c1, sorry here, oh, I keep mixing it up. c2, this will become 0, because c2 is equal to 0 times x squared, plus, now we're going to find c3, and c3 we found was negative 1 over 3 factorial, so we can replace this plus with a negative since it was a negative value. So it becomes negative 1 over 3 factorial times x to the power of 3. And then let's just do 2 more until you should see the pattern evolving, or emerging, sorry. And then that's going to be plus 0, oops, plus 0 x to the 4th, and then one more time, since this one was negative, this one must be positive. It becomes 1, like that pattern we found, it's this plus the bottom plus 2. So it's 1 over 5 factorial times x to the power of 5. Wrong color, and it was ugly. Then we should see that result here. And if we kept writing this, it would keep following that pattern. Okay. Well, let's do some adjustments to this. We can notice every other term here collapses to 0. 0 times x squared, I don't care what x is equal to, it'll be equal to 0, because anything times 0 is 0. So then we can remove all these terms. So then it becomes m of x is equal to x. Actually, let's write that one there just to make it more obvious. X plus, actually that's the wrong color too. Plus, that 0x squared, that disappears, right? So then it becomes negative 1 over 3 factorial times x to the power of 3. And then that's going to be plus, we skip this term here because it's a 0, collapses, plus 1 over 5 factorial. And that's going to be x to the power of 5. And let's just do one more. Plus 1 over 7 factorial. And actually it would be negative because the last one was positive. X to the power of 7. And then so on. So this is just us simplifying. These two are equivalent. We just remove the terms that don't contribute much. Okay. So now that we have this representation, what patterns can we notice? Well, like last time, we saw that it alternated from plus or negative, so let's write that down. So plus or negative, and let's just use a blue to show that it loops. Okay? Another pattern is these two increase by 2 every time. Okay, so then that's, let's write n factorial, which is just like the bottom here, because it changes all the time, so let's just use a variable. N factorial increases by 2. So, okay. And then the same thing with the exponent. So x, whatever you have at the top here, increases by 2 every time. So go, so this one is a 1. So 1 plus 2 is 3. 3 plus 2 is 5. 5 plus 2 is 7. So it would be, let's use it again, is times 2. Okay, so now that we're noticing these patterns, and since this is an infinite series, because every time your exponents are being increasing and your factorials, so this series will never end actually. So let's put into summation notation. And we'll actually skip the summation for now that I think of it. All right, it'll make things simpler. All right, so first of all, how do we express this plus or negative? Well, what we can do is take, consider this. Anything to the 1 to the power of anything will always be equal to 1. So 1 to the power of 5 million, 1. 1 to the power of 0, 1. 1 to the power of 3, 1. So that can be used here because we don't want there to be any coefficients. 1 to the power of anything will stay there. Now this might be confusing, but let's just add a negative 2 in front of the 1 here. So now consider negative 1 to the power of n. And now something neat happens. So if we set n equal to 0, then negative 1 to the power of 0 is just 1. Okay? So this will be equal to, actually that would not be right, is equal to 1. And if we set n equal to, oh, that's ugly, n equal to 1, then negative 1 to the power of 1 is equal to negative 1. Right? And then let's do it one more time. Oops. N to the power of 2, or negative 1 to the power of 2, sorry. This will be equal to 1 again. And if we were to do it again, it would be negative 1 if n was equal to 3. So depending on what n is, it'll be equal to 1 or negative 1. And this is like what we wanted, alternation between positive and negative. So we can use this depending on what n is to make a term either negative or positive. And we can just multiply it by the term so it makes it negative. Okay, so that should be in our equation, our summation equation. All right, so let's write that down. Negative 1 to the power of n. Actually, yeah. Negative 1 to the power of n. All right. Okay, that's only part of the problem. Next, we notice that our factorials at the bottom are increasing by 2 every time. Okay, well, simple fix. It would be this divided by 2n factorial, right? So if we set n equal to 1, that would be negative 1 to the power of 1. That would be negative 1, negative, so this term would be negative. And then 2 times 1 factorial is just 2. But then we encounter an issue since these are odd numbers. when we want odd numbers, not even numbers. So then we have to add a +1 at the bottom here. Okay. Now the last part is this x, where the exponent increases by 2 every time. So then that becomes, x to the power of 2n and then remember our exponents were also odd every time it existed. So then that would be +1 as well. Because anything even +1 would be odd. Alright, so we have this equation here. So let's now write the summation piece. So, n is equal to 1. And then the top upper bound is infinity. And let's see if this works. Okay, so let's set n equal to 1, so -1 to the power of 1 is negative 2 times 1 plus 3, so this becomes -1 over 3 factorial times x to the power of 3. And it looks like it works. It matches this term here. And then if we set it to n is equal to 2, then that becomes 2 times 2 plus 1, 5 factorial, and then the exponent, or I mean the numerator, -1 to the power 5, or sorry, -1 to the power of 2 is positive, so that's 1 over 5 factorial times x to the power 5, and that actually matches what we have here. So this summation piece works. But there's one issue, and that's we skipped over the first term. So everything works except that we missed this term, that 1x1, and we can just simply mend that by doing this, x plus this summation here. And here we go. This, what we just found here, is equal to sine of x. Congratulations, we finally found what sine of x is equal to. But we used infinity in the upper bound here because we need infinite terms to represent sine x, because it has infinite derivatives. Because of that derivative idea, the derivative loop I showed you here. No matter how many derivatives you get, you just keep looping and looping and looping. But your approximation gets better as your upper bound gets better, and your approximation gets perfect once it reaches infinity. So this is all equal to sine of x. And we did it. Now we can simplify this, and it's a bit messy right now. We can pull that x in by simply just doing this. So instead of n being equal to 1, we can make it equal to 0, so that's where we start. Then upper bound is always infinity because our approximation gets better and better as you add more terms. And then everything inside is just the same. So negative to the n all over 2n plus 1 factorial times x to the 2n plus 1. And if you just set that beginning bound to 0, so -1 to the power of 0 is 1, and then 1 factorial is 1, so that becomes 1 times x, because that 2 and 2 times 0, 2x to the power of 1 is just x, so that becomes x, and that's how we create this term. So this is actually how you would usually see the definition. These two are equivalent, just this one's simplified. And let's just do that same piece. This is equal to sine of x. All right, interesting. That's how we do it. Now let's generalize our Taylor or Maclaurin series formula. So remember how we wrote m of x is equal to c0 plus c1 times x plus c2 and so on, okay? How would we generalize this in the summation notation? Well, if you remember, if we took m prime of x, you applied the power rule here, right? And you'll notice that every time you take a derivative of something, right? So let's say for suppose x to the power of 8, and you took the seventh derivative, or actually, yeah, the seventh derivative, or actually no, let's go eighth derivative. It would become 8th factorial. So as you keep applying the power rule to this Taylor series, it kind of gets poisoned by all these power rule products coming down from the top every time you apply it. And this can be problematic because it shifts your result, and that's why we had to do all this algebraic on the side here, 1 over 5 factorial, negative 1 over 3 factorial, and all that. And that's why we had to cancel it out. So let's generalize this. So let's write the summation notation. Okay. So your Taylor series will be equal to m of x, and it'll be equal to f, and I'll explain this formula after I write it down. Divided by n factorial times x to the power of n. And this approximation gets better and better as you add, and then n is equal to 0. Perfect. And let's just, no, we're good. Okay. So what the hell does this mean? So again, this idea of your power rule poisoning it, that's why this n factorial down here is there. So it can cancel out all that poisoning that's occurring every time you take the power rule. And this f to the nth derivative of 0, remember how we said we were centered on 0 for Maclaurin series, right? How we took sine of 0 and all that. Oh, formatting issues. Sine of 0, and that's where we centered it. That's why we have our f to the nth derivative. So pretty much what we're saying here is, let's start at 0. So let's say the function we want to replicate, let's just start with what we already had, right? F of x is equal to sine x. Right? So what this is telling us is, okay, start at n is equal to 0, and so that would be f here of 0, which is just f of x, because your f of 1 is your first derivative, so it would just be f of 0, and it would ask you to evaluate what f of 0 is, and f of 0 and sine x is, remember, 0. Okay, and then it says n factorial, 0 factorial, okay, is equal to 1. Okay, and then x to the power of 0, anything to the power of 0 is 1. So then that becomes times 1. So then it tells us our first term of our series here is 0, because 0 times 0 divided by 1, right? What we're following instructions here, 0 divided by 0 factorial, which is 1, this is equal to 0, which matches our first term we found in our whole list here, right? First term is C0. Okay, and let's do n is equal to 1, right? And this might be repetitive, but just to understand what the hell this formula means. Okay, so f first derivative, right? Because now we're done with 0, we're at 1. F of 1. Well, what is derivative of sine x? Is cos x. So let's just write this. So we're literally doing the same thing as before, but it's just this formula is a little bit abstract. Okay, and then f of 1, 0 is equal to just 1. So how would we write that? So then this becomes 1, right? This first part, and then 1 factorial. So it becomes 1 over 1 factorial times x to the n, and n is equal to 1, so then it becomes 1 over 1 factorial x times x, and that becomes 1x. Okay? And then that's our other term, and that matches what we again did with m of x, right? Plus 1x, and that's what it says here. And if let's just do it one more time just in case you're still not sure. F of second derivative of x, let's just do this quickly, is equal to negative sine of x, and then f double prime of 0 is equal to 0. 0. F double prime of 0 is equal to 0. All right, now that we have this, right, so then it becomes 0 over 2 factorial times x to the power of 2. And then again, this cancels out, and 0 times anything is always equal to 0, and that will match what we found here, right? 0x squared. So this formula, this neat formula, works for that. And this is what you use if you're to try to find other functions. So if I tried telling you to find a Taylor series of cosine of x, or some other function, you'd use this to know what to do. Instead of writing out these elaborate things, pretty much this is what just saying, this n factorial here is just telling you it's canceling all the power rule. Okay, now let's move on to Taylor series, and this will be brief. So if I asked you to build a Maclaurin series of the function natural log of x, you would follow your normal steps, right? So you'd do that long list of things, right? M of actually actually, let's just follow the formula that we used, because I just said that's why we use it. So then it would be that summation, and then f. So f of x is equal to this, right? So then it asks us here to find the first, to find the 0th derivative. So that's just the original function, as I said right here, right? Of 0. So evaluate at the point 0. That's what it's telling you. And I don't know if you know this, you should, but natural log of 0 is kind of problematic. It's undefined. So the natural log of 0 is undefined. So our Maclaurin series won't work here because it's centered at 0. So we're going to have to center it at somewhere else where that isn't undefined, right? And the natural log of x is only defined for when x is greater than 0. Negative numbers, that's in the complex plane, and 0 is just undefined. It's an asymptote. So let's try something else. So instead of being centered at 0, let's just center it at 1. Okay? So let's write our series again. And the reason why we're not writing this formula down again is because it won't work, as we saw. So let's just make this brief. M of x is equal to c0 plus c1 times x plus c2 x squared plus, and so on. Okay, don't have to add. We already know what's going on here. So if we were to center it, as I said, at 1, right, a problem happens. So, right, so if we were just to find c0, right, we would do m of 1 here, right? And unlike our Maclaurin series, it doesn't collapse. So it'd be c0 plus c1 times 1, because we're centered at 1 here. Plus c2, and then that'd be bracket 1 to the power of 2. Oops. So these terms don't collapse, and these other terms here pollute. We're adding derivatives that shouldn't be there, if that makes sense, right? And our sine, where it was centered at 0, all the other terms would collapse when we would make it equal to 0. M of 0, right? C1 times 0 when we replace x with 0, because x is equal to 0 for this. All of these terms collapse. But that isn't the case down here. They stay here. So how can we make these terms collapse? And we can just do it by a simple algebraic manipulation. We would do m of x is equal to, that would be c0, so this stays the same, plus c1 bracket x minus a. And I'm just not using my colors properly here. X minus a plus c2 bracket x minus a squared plus x minus a cubed, and so on, right? Hopefully you can see the pattern. Okay. And with this a here, a is where it is centered. Oops. And that's what a Taylor series is. A Maclaurin series is a type of Taylor series, but a Maclaurin series is centered on 0, so a is equal to 0. But a Taylor series can be anywhere, including 0. So if you think about it, sine of, when we did the sine one up there, we set it as a Maclaurin series, a to e 0, and that makes sense here because x minus 0, right? A is equal to 0. X minus 0 is just x. So actually, though that a term, was hidden from us because it collapsed away to x. This is when we set it to 0. But when we set it to something else, it does not collapse. And this might not be too intuitive, but it should make sense once we slightly work with it. So we said it was centered at 1, right? So that means x is equal to, or a is equal to 1. And if we do the same thing here now, so let's say for this case, a is equal to 1, then that becomes mx is equal to c0 plus c1 bracket. Well, it's actually just the same thing up here, so let's just, so actually, no, I am incorrect. All right, c1, and that's me x minus 1. And then that pattern repeats here. It would be plus c2 times parentheses x minus 1 to the power of 2, right? And if we evaluate, again, m of 1, what you'll notice this time is that in all of these brackets, all the x minus 1's brackets, right? All the x minus 1 brackets, when you evaluate x to be equal to 1, it collapses again. So when x is equal to 1, it becomes just 0. So then we reintroduce that collapsibility, and now our Taylor series will work again. So let's just write what that would look like here. So that would be equal to, that would be c0 plus c1 bracket 1 minus 1, right? And then you'd add all of those other terms. And now when we evaluate at 1, like in our sine x up there, our Maclaurin series of that, this term cancels out to 0, collapses to 0. c1 times 0 is 0. So then now, no matter what comes after this, all the other polynomial terms, this collapses, and this goes away. And now we're just left with c0. And if we took the derivative of this, the same thing would happen. So that's the beauty of this. So if we were to take the derivative of that, it would become all messy, and it would just not fit in this video. It would get very algebraic if we started trying it doing this way, but just know that it works. So the formula, like the Maclaurin series here, the simplified version here, is quite similar. It would be like this. So that would be x minus a, and that would be bracket f n, and that'd be over n factorial times x, x minus a. And this all becomes in a bracket. Lower bound is equal to 0, and our upper bound is infinity. So this is your formula for a Taylor series. And we just have that a there. So the only difference between this one and the other one is the x minus a part, where a was equal to 0 in the Maclaurin series, so just x instead of x minus a, because minus 0 is just redundant. Okay. So that's how we could solve a problem, is just by skewing it, or skewing our centered point. So now it actually works, because if we just used our Maclaurin series, it would not work. So that's the use of a Taylor series, just a bit of an adjustment over a Maclaurin series. So that pretty much finishes the video. However, what's the point of all this, right? What's the point of a Taylor series or Maclaurin series? I mean, yeah, we found what sine x is equal to, but there's other ways of approximating sine x using different methods. So what's so special about a Taylor series? And the answer is, it's mostly in computational engineering. So when you ask your calculator, what is sine of, I don't know, 2 pi 4, something like that, right? Well, you don't know how to calculate that. But what the calculator does is it uses a Taylor series, and it just crunches up all the numbers here. So it literally does a Taylor series expansion, like right here. It makes all those terms, right? And it just substitutes that 2 pi times 4 for x. And then whatever value it gives, that's the value of that equation, I guess. So that's, computers use Taylor series to compute functions like these. Same thing with natural logs, right? How the hell would you calculate a natural log? Well, it uses Taylor series as well. It uses other methods like lookup tables and Newton's searching method, but one of the predominant ways that your calculator, your TI or whatnot, calculates is using Taylor series, since, as I said, it's easy to compute, I don't know, 4 to the power 4 or 2 to the power 4. This is just, it might be time consuming, but it's simple arithmetic. And that's why a calculator can do simple arithmetic very easily, very quickly. And that's why it uses Taylor series, because it's literally just arithmetic, repetitive arithmetic. Another trick they use is a problem with Taylor series, not really with sine x, but more of exponentials and logarithms and discontinuous functions, is when you add a lot of terms to your Taylor series. So you say your upper bound here, because a calculator can't do infinite terms, right? It'll just do some really big number up for its upper bound for a really good approximation. And what the problem is, if you go too far out, if you set x, let's say, and you tell your calculator to find the approximation, let's say you set x to equal to 5,000, right? It's gonna be so far away that our Taylor series won't have reached that point of approximation properly. And the best way to show this would be on a graph on Desmos. However, yeah. So if you were to, let's say, use a Taylor series to represent your sine function, a Maclaurin series, pardon me, right? So near the origin, it might look like this, but then it'll go like this on the edges. And here, these are where your approximation values are poor. As you add more terms, your approximation here gets better, so it's going to start looking like this, but then you'll reach another point. So if you plug x as a really big number, then you get somewhere like right here on the graph, which is not a good approximation. Your best approximation is where your point is centered, right? So a big thing about Maclaurin series is wherever your function is centered, right? So that sine example we used, it was centered at 0. At sine 0, that's where its best approximation is. As you stray away further and further from that 0 point on the graph, the x is equal to 0, your approximation gets worse and worse and worse. And that's what you see here with these, how these curves suddenly just diverge like that. And a way calculator, instead of doing like 10 million different have an upper bound of 10 million to reach that far, what it uses is actually a Maclaurin series where it changes its center point to that of what you plugged x. So if you asked for example, sine of, I don't know, 10 to the power of 24, right? That's a really big number. You don't have to have an upper bound of some stupid number to make these curves reach all the way that far out. So what it does instead is set its a value equal to this here. And since it's centered there, your approximation gets really good. And that's the same thing for natural log. If you graph a natural log using a Taylor series approximation, right, it'll probably look something like this. It'll look good and then it'll go back down, right? So if you ask when is x is equal to 4, then you'll find something all the way down here. And that's a really bad approximation because in reality, a natural log graph looks like this. So that's a limitation of a Taylor series, but also how you can mend that limitation. And before we finish, another cool thing about a Taylor series is the following. If you ever wanted to compute what Euler's number is equal to, right? Euler's number is equal to 2.7 ... But what's a way of finding what Euler's number is? It's an irrational number. And one of the cool ways is actually using a Taylor series. So this is how they did it. So consider, let's go e to the power of x, right? This is equal to f of x. Right? Okay, that's f of x. Okay, well now let's use our Taylor series and let's center it at 0, since that just makes things a lot simpler. So remember that formula right here, right? Okay. So it's going to ask us f of 0 actually it would be the 0th derivative because we start with the 0th derivative. F of 0, right? So we just plug in x with 0, right? E to the power of 0 is equal to 1. So this should be equal to 1. Okay? So remember our formula, let's just write it down again just because it's so far out. So if you remember, it was f n bracket x, this is for a Maclaurin series again, all divided by n factorial times, oops, and that should not be f of x, should be f of 0 times x to the power of n. Right, and then n is equal to 0. And then our upper bound is infinity. Right, this formula. So we want this to be equal to e to the x. So, right, so first we're going to evaluate what f of at 0 is, right? So f of 0, right? And that's equal to 1. Okay? And then 0 factorial. So the first term, C0, should be equal to just 0, or oops, should be 1 over 1 factorial. So that means C0 must be equal to 1. Okay, let's move on. Remember our steps. Okay, now it's going to ask us n is equal to 1, not n is equal to 0 anymore, because we're done with that. And remember, x to the 0 is 1, so that would actually becomes 1 over 1 factorial times 1, which it all stays the same. Okay, n is equal to 1. Now let's do the same thing. Well, what's the derivative of e to the x? Well, that's a hard one, man. E to the x. Okay, and then we start that thing again. F of 0. So that becomes f, oops, wrong color. F prime of 0, again, is going to be equal to 1. Okay, and then we follow that rule again. So, and this should be 0 factorial, oops. Okay, well, C1 is going to be equal to C1 is going to be equal to brain fart. It's going to be equal to 1 as well. Now let's do, because it's going to be 1 over 1 factorial times 1. Or times x. But that we're just looking for the constant, not the x. So this x is actually kind of useless for now. But we'll just keep it there since it's our formula. All right. So next, it would be n is equal to 2. Okay, well, there should be already a pattern here, right? So then we take the derivative of e to the power of x, right? And that just stays e to the power of x, and then we replace, or we evaluate x is equal to 0, and that'll be equal to 1 again. Okay? So we know that this upper bound here will always be equal to 1. Always be equal to 1. And then it's just going to be n factorial. So n factorial is 2 factorial. Okay? And then let's do it again. Derivative of e to the x equal to e to the x. E to the power 0 is 1. Okay, and then it's going to become 1 divided by, well, n is equal to 3 this time. So it'd be 1 over 3 factorial. So your series is going to look like this. So m of x is equal to, it's going to be equal to 1 times x, or 1 plus 1x plus 1 over 2 factorial x, oops, squared, oops, what am I doing? Okay, plus 1 over 3 factorial x cubed. And this is our series. So we notice that our derivative here is always going to be equal to 1. So let's just replace our derivative here, f to the n 0. So we know that it's going to be like this. Since f of n to the power evaluated at 0 will always be equal to 1, right? Derivative of e to the x is always equal to 1, or e to the x is equal to e to the x. And when you evaluate, it's equal to 1. So we can just substitute that. So it just becomes 1 times x to the n, which is x to the n over n factorial. And here's something beautiful happens. So now that we know this is equal to, let's just copy this. Did not mean to move it. And paste. Okay. Since we know this is equal to e to the x, so e to the x, sorry, it's a little close to the wall there. E to the x. Well, what if we wanted to find what e is? Well, what do we have to replace x with to make it just equal to e? Well, x is equal to 1. Right? Because e to the power of 1, right? X is equal to 1 is just equal to e. Euler's number. So, let's represent that in our summation notation. And infinity. N is equal to 0, right? This stays the same. But then it becomes bracket. So x is equal to 0, or x is equal to 1. So that becomes 1 over n, or to the power of n, sorry, divided by n factorial, right? The n factorial does not get affected. And then close bracket. And 1 to the power of anything will always be equal to 1. 1 to the power of 8 million, whatever, always equal to 1. So we will find that Euler's number is equal to the summation of 1 over n factorial, close bracket, n is equal to 0. Oops, wrong color. And you'll find that Euler is equal to this summation piece. If you plug this into your calculator, you go to your calculator, you'll see that this approaches Euler's number as you add more terms, as you make the upper bound bigger and bigger and bigger. And this is one of the reasons why Euler's number is not a rational number, because you need infinite terms here to represent it. So go ahead, plug this in your calculator, and you'll see that this is equal to Euler's number, which is really neat. Because Euler's number is like pi, right? It's transcendental and it's special. So there we go. That cuts it for the video. This is what a Taylor series and Maclaurin series is, how it was found, how to use it, what it's used for, cool cases down here, why polynomials are amazing, and their uses, power rule, and our cool mimicry idea. It's just, I love Taylor series and Maclaurin series. It's a great part of math, and it's simple for what it is, what it represents. It can do so much, but it's not that complicated, and it really is a beautiful masterpiece of math. This was my first video. I hope you guys enjoyed. I hope it made sense. I hope it wasn't too boring or too abstract. I tried to make it as clear as possible, but I hope you enjoyed it. Yeah, thank you for listening. Goodbye.